Hello everyone, this is Aditya and today we are going to start with the second lecture of special theory of relativity, and in this we are going to study non-variance of Maxwell's equations under Gaussian transformation, and we will be studying Michelson-Morley experiment in this. So let's start with the lecture, but for that please do like, share, subscribe and please support this video. Now let's start. Okay. So, non-variance of Maxwell's equation under Gaussian transformations. Let's see that. So before this, let's recall something from lecture 1. Principle of relativity. I think I did not told the exact definition that time. I just told uh, that line, that much I told, not the exact term for it. Okay, so let me tell that. So what is principle of relativity? Laws of nature are same for all inertial frames of reference. So basically it is that laws of nature are same for all inertial frame of reference, and which we had proved also when we had proved F is equal to ma, when we had proved the second part, the invariance of Newton's laws of motion under Gaussian transformation. In that we had stated this statement, right? So this is the principle of relativity. Okay, not a special theory of relativity. Of course, it is the first postulate of a special theory of relativity, but a special theory of relativity includes one more postulate which we will discuss in some time. Okay, so right now let's understand Maxwell's equation. Of course, we won't go into that because that is a topic for actually it requires another series itself. So what is Maxwell's equation? Let me write it. This is the del operator, we all know it. The divergence of E is equal to rho by epsilon naught. Okay, and curl of E, this is E, maybe I said B or whatever. Okay, is minus dB by dt. This is the vector. Okay, and divergence of B is 0, and curl of B is equal to mu naught j vector plus mu naught epsilon naught d e vector by dt. So this is these are the four Maxwell's equations which you must have studied. Sorry, just give me a minute. Yeah, so this is the equation, and instead of d you can say it as partial derivative, right? Because b includes more factors too, right? So this is what is required over here. So these are the four Maxwell's equation, and when you combine them all you get a wave equation. What is that wave equation? Is equal to 1 upon c square del 2 e by del t square, and this is of course dot product, is 1 upon c square times del 2 b by del t square. Sorry, not vector. Okay, so this is the wave equation form of Maxwell's equation, right? Okay, now suppose there is a light beam and all, right? That is very obvious thing if we are studying Maxwell's equation. An electromagnetic wave, I should say, right? So this equation should be valid for all inertial frames of references, right? But there is a problem. And what is the problem? The problem is that suppose if there is a frame which is moving with a velocity v, and this is this particle is moving at the speed of light, right? Okay, so this is basically wave motion, whatever you want to say. I'm not going to into that right now. Okay, suppose light is moving at the speed of light, of course. So what will be the speed of light over here? Suppose this is x dash, y dash, this z dash, and this is, of course it should be over there, but still this s and this s dash frame, this is at rest, right? This is at rest. So v x prime will be equal to what? Vx minus v from the Gaussian transformation for velocity. So it means that it will be c minus v with respect to s prime frame of reference. So it means that the speed of light is not constant for all initial frames of references, which means that Galilean transformation is not applicable for all initial frames of references, since the velocity of light is not same for all initial frames of references. So it actually contradicts the principle of relativity. It states laws of nature are same for all inertial frames of references. But now Maxwell's equations are getting violated over here. Why? Because of course the speed of light is not same for all inertial frames of references. So this equation is not valid for all frames. It is only valid. Uh, it tells that the speed of light is c, right? So what to do in this case? This is a big question. So it means that either speed of light is not constant really for all initial frames of references, or second thing is that the principle of relativity is wrong. So what is the truth? Maybe Galilean transformation is not correct. This is not true. Under Galilean transformation we need another transformation. Under that it may hold, or it is also possible that it may not hold. We have to check for it. So basically the idea is that under Galilean transformation Maxwell's equations are not valid. So this is a big problem for principle of relativity, right? So now what is the solution for it? Well, Einstein said that let's assume that the speed of light is constant for all frames of references and for all inertial frames of references, and then he made all his calculations, and that is the second postulate of special theory of relativity. But we aren't going into that. First of all, let's understand how this thing was proved that the speed of light is constant for all inertial frames of references. Let's understand this first of all. And if you don't know what is this del sign, let me explain. Del is actually there's a differential operator with respect to position. Okay, like this it is. Okay, so now let me erase this and let's move to the idea how it was proved that speed of light is constant for all inertial frames of references. Let's see that. Let me erase this first of all. So now let's study something called as Michelson-Morley experiment. Before going into this, let me tell you a story behind this. So when this debate was going on under Galilean transformation, Maxwell's equations was not valid. So an idea was proposed regarding ether. And when calculations are made under ether frame of reference, ether inertial frame of reference, then in that case the speed of light is actually c, and under all other experiments of in all other inertial frames the velocity will change, the speed of light will change. So it was assumed to be as absolute inertial frame of reference, and of course it was assumed to be at absolute rest. This was the thing. So when calculations were made under this inertial frame of reference, then Gaussian transformation, then Maxwell equations hold under Gaussian transformation. But when the calculations are not made in this inertial frame of reference, then Gaussian transformation won't hold. Sorry, Maxwell's equation won't hold, or we have to change the Maxwell's equation. Now this was still a contradictory statement. So how it was disproved? Let's understand this. So for that, Michelson-Morley experiment was done, but the aim was different. The aim of Michelson-Morley experiment was to find velocity of Earth with respect to ether frame of reference, ether inertial frame of reference. Okay, this was the aim of the experiment, but this experiment badly failed. So it proved that the speed of light is constant for all frames of references, all inertial frames of references. So this is what was aim, and the conclusion was different. Now, how we'll find the velocity of Earth with respect to ether frame of reference, ether inertial frame of reference? Let's understand this, but first of all, let me raise this. Okay. So there was a simple setup which they had used. A very rough diagram I'll be drawing. Let me take another chalk too. Yes. So suppose this is a glass sheet, okay, and suppose there is a source of light somewhere, so it is directed towards it, and there is a mirror over here. So light goes, we have placed it at the angle that the light goes perpendicular to this, and of course not all light will get reflected, some will get transmitted, so it will go like this, right? And of course if the light is, suppose this is mirror 1 and this is mirror 2, and if the light is going towards the mirror, so of course it will strike back and will go like this. Some light will go back and some will go over here, and similarly some light will go and some light will return back, and it will go like this, and some will go towards this direction too. Now here they had placed a telescope, for reading. No, I will tell the use of telescope. Okay, so this was the source, and remember one thing, that this whole setup was actually floating over mercury liquid, I guess. I don't remember exact thing, but that was the thing. It was so because so that they can rotate the whole setup. So I will tell you in some time what is the use of that. So suppose this is Earth, okay, and suppose it is moving with a velocity v, okay. And suppose this is ether frame. Let's name it as S frame, and Earth has S dash frame. Okay. So what will be the speed of light with respect to Earth? It will be, from the Gaussian transformation of velocity of light in the frame of reference of Earth, S dash frame, will be Vx minus V. Now in this it should be C, the speed of light, minus V, correct? Okay. So when light is going in this direction, in this direction, then in that case the velocity which will be observed on earth, it will be this. So it means that when light is going in this direction for m1, when light is going in this direction, okay, in this case suppose this is t1a, whatever you want to assume you can, but since I am assuming this as event a, and when it will bounce back then we will assume it as event b. Okay, t1a will be equal to, suppose this length is l. Okay, so it will be l by c minus v, right? Okay, and t1b, this for both. Now this is related for this one. Now t1b will be l by, for returning back. So if the light, if this is the velocity and light is going in this direction, then what will the velocity in this case? Well, in this case vx prime will be negative c negative v. So negative c plus v, right? This will be the speed of light with respect to s dash frame. Okay. So it means that, of course, negative is telling that the velocity will be in that direction. So it will be c plus v, right? Now what is the total time elapsed in going from this point? Suppose this is O to A. What will the total time in going from O to A and then returning back? It will be, let's name it as O dash. And so total time will be T1 is equal to T1A plus T1B, right? So T1A is equal to L by C minus V plus L by C plus V, which is equal to, let's evaluate this. L can be taken as common, and when you solve it you will get 2c by c square minus v square. Just evaluate this, you will see yourself. Okay, now you can take c square as common, so you will get 2l by c into 1 by 1 minus v square by c square. This is t1. Okay, so this is t1. Now what is t2? Let's calculate that also. So let me erase this part so I can teach you that. Now for mirror M2, light is going in this direction upward and then coming down. Okay, this is the direction of light. Okay, so of course this is y-axis, this is x-axis, right? Okay, so vx prime will be equal to vx minus the velocity. Okay, now what is the velocity along this direction, along x direction? It will be 0 because the light is moving in vertical direction, right, in y-axis. So this will be 0 is equal to vx minus v. This is the x component of light. Okay, this is the x component of light, vx. So vx is actually equal to the v. Okay, now what is along y-axis? So we know vy prime will be equal to vy, right? Okay, now what will be the speed of light? Well, c will be equal to square root of vx square plus vy square, right? The velocity in the frame of reference of ether. So the x component of light and y component of light. Okay, so what is vx? Vx is equal to v, so v square. And what is vy? Vy is equal to vy prime square. This is the velocity of light which will be observed. So vy is equal to c square minus v square, vy prime. So this will be the velocity observed by the observer in S prime frame of reference, right? So it means that from, let's assume this length also as L. So from going from O prime to B, the time taken will be L by square root of c square minus v square, and in returning back it will be still the same. Why? You can solve it easily. The same mathematics will be there, right? That's it. Okay, so now let me erase this, and let's first of all calculate total time. So it is t2 because this is for mirror 2. T2 is T1 T2A plus T2B, right? So let's calculate this. It will be 2L by square root of C square minus V square, which is equal to L by C times 1 by square root of 1 minus V square by C square, right? So this is T2 and this is T1. Okay, now let me erase this all of these things except this, and let me write these two results, and then I will tell you further. So we had got T1 is equal to 2L by C into 1 minus V square by C square, and T2 is equal to L by C into 1 by 1 minus V square by C square square root. Okay, we have got this. Now what is the time difference between these two events? T1 minus T2. Let's define as T1 minus T2. So it will be 2L by C 1 by 1 minus V square by C square minus 1 by square root of 1 minus V square by C square. Now due to this time difference, some fringe patterns are observed on telescope. Fringe patterns are observed. This is the gap, the dark fringes, this is the bright fringes and all. Okay, now I told earlier that it was made to float on that mercury liquid, I guess. Okay, so what Michelson and Morley did, they rotated this whole setup by 90 degrees. So what? When they rotated it by 90 degrees, this M1 became perpendicular, and this M2 came in along x-axis, right? So whole story changed. Now what will the delta T star when it is rotated by 90 degrees? When rotated by 90 degrees, it will be T1 minus T2, right? T1 minus T2 star. Again the calculation will be same, but now this M1 is now in perpendicular direction, so it will be 2L by C 1 by square root 1 minus V square by C square minus 1 by 1 minus V square by C square. Now this will be just negative of this. Now due to this change in time difference, delta T minus delta T star, it is actually 2 times delta T, right? You can observe it clearly, right? It is actually this. Due to this difference of time difference, there should be change in fringe pattern. It should shift. But when the experiment was done, there was no shifting of fringe pattern, which means that since no shifting, which implies delta T is equal to delta T star, and it ultimately means that the velocity V should be equal to 0. Then only these two quantities can be equal to 0. It means then only these two quantities can be 0, right? Basically this is negative of delta T is actually negative of delta T star. So it means that if they both have to be equal, then what will the case? These two have to hold simultaneously, which implies that velocity should be equal to 0, correct? Right? The velocity of Earth with respect to ether, the frame of reference of ether, it should be 0. Okay, so Michelson and Morley thought that maybe uh, this month when they were doing experiment, maybe that the Earth is moving is moving in such a way that it is at rest with respect to the frame of reference of ether. So what they thought, let's do it again after some months. So this experiment was performed throughout the years. I mean, I guess 1 year or 2 year. I don't remember exact time, but it was done through years in different months. And all of those cases, there was no shifting of fringes. There was no changes. There was no shifting in fringe pattern, which ultimately proved that sorry, that in whatever month you are trying to do this experiment, there is no shifting of fringe pattern, which ultimately means that the velocity of Earth should be zero. But that is not the case. We know it. Velocity of Earth cannot be zero always with respect to the frame of reference of ether. So from here, there was a long debate, and then came Einstein, and he said, stop thinking all this. Just assume that the speed of light is constant for all inertial frames of references, and rest all the calculations will be done according to that. So from here, it was ultimately proved that it was not proved actually, but it was the null result of Michelson-Morley experiment. So Einstein said, first postulate of special theory of relativity. It is the principle of relativity, that is, which was given by Galileo or Newton. Okay. Second was speed of light, and when I say speed of light, I mean speed of light in vacuum. So let me mention also, in vacuum is same for all inertial frames of references. This second postulate was very important, and when we use this concept, then everything was okay. So this is what I wanted to teach in this lecture: Michelson-Morley experiment and non-invariance of Maxwell's equations under Galilean transformation. So in next lecture we will be studying Lorentz transformation and time dilation thing, and then we'll move on slowly and steadily. Okay. So I hope you enjoyed this lecture. If you did, then please do like, share, subscribe, and please support this video, and I'll be soon uploading lecture number 3. Bye bye, take care.